Hi, in this video we're going to be talking about derivatives of parametric equations. So we're going to be talking about how to get tangent lines, and on the way we're going to be talking about how to actually get the derivative, dy dx, and we're also going to talk about concavity. So let's go back to single variable stuff without a parameter, and say we have a function y equals f of x. Now, the tangent line at a point x equals a is going to be y equals f of a, which is our height at that point, a plus m times x minus a. And the important part here is that m is equal to f prime of a, our derivative. But f prime of a is equal to f prime of x at the point x equals a, which is dy dx at x equals a. Now, let's transition to parametric curves. So we want to use the formula, this guy up top here. We want to use this formula since then we can use our parametric equations to find the x and y coordinates of the point. So let's talk about how to actually do that. So for our derivation, we're going to eliminate the parameter and then put it right back in. And we're going to use the chain rule along the way to actually figure out what our derivative is. So let's have x and y be parameterized by t. That is, x is a function of t and y is also a function of t. So if we were to eliminate the parameter, so eliminating the parameter, say for x, so we get y equals some other function of x. But y is also a function of t, so let's replace y with g of t. So g of t is equal to big F of little f of t. So let's go ahead and look at dy dt, which is going to be g prime of t. And this is going to be, by the chain rule, big F prime of little f of t times little f prime of t. And we know that f of t is x, so we get big F prime of f of t times dx dt. Now remember that we're looking for dy dx. So we know that dy dx is equal to dy dt over dx dt. If we were to treat these differentials as numbers, they would make a lot more sense. So let's go ahead and do that for a brief moment. And if we were to multiply both sides by dt, top and bottom, we would get dy dx. So now we have two fundamental formulas for our derivative. We have our standard one that we are normally used to, dy dx. That's going to be dy dt over dx dt, provided that dx dt is non-zero. Otherwise, we'd have a 0 in the denominator. And if necessary, if we have x as a function of y instead of y as a function of x, what we're going to have is dx dy, which is going to be dx dt over dy dt, provided dy dt is non-zero. And these conditions here just ensure that we're not dividing by 0. So now let's take a look at an example. So we want to find the tangent lines for x equals t cubed minus 5t squared and y equals t cubed plus 1. And we want to find this at the point 0, 1. Okay. First, let's take a look at the question. It's asking for the tangent lines and not the tangent line. This is because we could have a possibility of our parameterization looking something like that. And if we want to look at it at this point, say, we would have a tangent line here, and we would also have a tangent line here, which is why we can't just say the single tangent line. We have to include possibilities for multiple tangent lines. So let's go ahead and just find dy dx. So dy dx is going to be the derivative of y with respect to t over the derivative of x with respect to t. So this is y prime over x prime, and the derivative of y with respect to t is going to be 3t squared. So we just put 3t squared in our numerator. Sorry, have a little bit of stupid tongue every once in a while. And then we're going to put dx dt in the denominator. So for dx dt, we have 3t squared minus 10t. Okay. Now, if we were to look at the point 0, 1, we would have we have to solve for t in order to figure out if this actually exists. So for x equals 0 and t equals 1, or y equals 1, we're going to have that t cubed minus 5t squared is equal to 0. And we're going to have that y, which is equal to 1, is going to be equal to t cubed plus 1. So in the first case, we have factoring out a t squared, we get t minus 5 equals 0. So t is either 0 or t is 5. Now solving for y, or solving for t in our y part of our equations, we have that t cubed equals 0. So t is just 0. So for our conditions here, we have to have that t is equal to 0. And in this particular case, there is no solution for dy dx. So there is no solution for dy dx at t equals 0. And that tells us that we have a vertical tangent line, right? So this tells us at the point 0, 1, we have a vertical tangent line. So that means it's going to be x equals something. So in our case, it's going to be x equals 0 is the equation of the tangent line at that point. For our final example, let's find the equation of the tangent lines, if any, and concavity of the curve given by t cubed minus 5t squared in our x component and t cubed plus 1 in our y component, which is the same one that we had before, except we have a different point. We have negative 4, 2. So let's first start by finding dy dx. So that's dy dt over dx dt. So as we saw before, it's 3t squared over 3t squared minus 10t. And now we need to find the points at which, we need to find the t value for which this point is satisfied. So we have t cubed minus 5t squared is equal to -4. And we have t cubed plus 1 is equal to 2. This tells us that t must be equal to 1. So let's go ahead, since this is our only possible value of t for the y's, plug it in to the x and make sure we get -4 out. So 1 cubed minus 5 times 1 squared is 1 minus 5, which is -4. So our t is equal to 1. So let's go ahead and take our derivative here and plug in t equals 1. And we're going to get 3 over -7, or -3/7. So now we have our slope. So m is equal to -3/7. So now we just have to find the equation of the tangent line, which is y minus y naught is equal to mx minus x naught. And here, x naught, y naught is going to be equal to our point, -4, 2. So y minus 2 is equal to -3/7 x plus 4. So y is equal to -3/7 x minus 12 over 7 plus 14 over 7. So y is equal to -3/7 x plus 2/7. And that is the equation of our tangent line. Now let's go ahead and look at the concavity. So for concavity, remember, we need to find d squared y dx squared, right? That's the second derivative. So we do have a formula. So d squared y dx squared. Well, that's going to be d dx of dy dx, right? And that is the t derivative of dy dx over dx dt. So let's go ahead and highlight this, because it is our important formula for concavity. So to find y double prime, we're going to take the tth derivative of what we already have, and we're going to divide it by dx dt. So the tth derivative, let's go all the way back up here and just paste it down here, right? This is dy dx. So, and then dx dt is just going to be 3t squared minus 10t. So we're going to have to use the quotient rule for the numerator. We don't really have to touch the denominator yet. So remember, it's low d high minus high d low over low low. So low is 3t squared minus 10t, and it occurs twice, so we square it. And then the top is the bottom, so 3t squared minus 10t, times the derivative of the top, which is going to be 6t, minus the top times the derivative of the bottom, which is going to be 6t minus 10. So we can go ahead and push this guy to the bottom, and we get 3t squared minus 10t all cubed. And on the top we get, well, let's just leave it where it is and plug in our value for t. So we're just going to copy this, minus 3t squared times 6t minus 10. And remember that we're looking for y double prime at t equals 1. So if we plug 1 in, we're going to get 3 minus 10 times 6 minus 3 times negative 4, all over 3 minus 10 cubed. Okay, so 3 minus 10 is negative 7. Negative 7 times 6 is negative 42, plus 12 over 3 minus 10 again is negative 7 cubed. Okay, so finishing up, we get negative 30 over negative 7 cubed. Okay, and we get 30 over 7 cubed. 7 cubed is 49 times 7, so that's 63. 7 times 4 is 28, plus 6 is going to be 34, so 343. So 30 over 343 is y double prime at the point given by t equals 1. So this is concave up. And its slope is, let's go all the way back, is negative 3/7. And we have negative 3/7 x plus 2/7 is the tangent line. Okay. And that is going to conclude our discussion on the derivative and the second derivative of parametric equations. Thank you for watching.